All right, we're back. We're on page 141. We're still talking complex numbers in trig form, polar form, sometimes rectangular form. What we're going to talk about now is how to raise them to powers. So this has a really, I don't know, it's kind of a memorable name at least. It's de Moivre's theorem. So de Moivre's theorem, maybe named after the guy who came up with it. You never know, or the person, I should say. I happen to know that de Moivre is a guy. But most things aren't actually named after the people who came up with them, so it's hard to know. So here's what it says. Sort of. It tells you how to raise a complex number to an nth power. So what I'm going to do is I'm first going to write z equals just r e to the I theta, because as with all things complex numbers, if you want to find a generalization, use Euler's formula, and the generalization just like drops out, and you're like, oh, got it. If you remember, we used it for sum and difference formulas. Now we're using it for this. Later we'll be using it for other things. It comes up a lot. So if I raise this to the nth power, so if I do z to the n, that's going to have to be r e to the I theta to the n. Okay, well that's going to be, so it's like a times b to the n is a to the n, b to the n. So this will be r to the n. And then e to the I theta to the n, a power to a power, you multiply the exponent. So this is going to be e to the, I'm going to write it as I times n theta. I mean, it's got to be I times n times theta, like however you want to group those. And then this, you can rewrite it. I guess I'll rewrite it down here. So I'm going to say it's r to the n, and then I'll use cis n theta. That's it. So it like could not be easier. Super, especially when they're already in polar form. So let's see if we can use it. So we want to do 2 cis 120 degrees to the third power. So r is 2 and theta is 120 degrees. So 2, so we're really doing, what are we doing? Oh yeah, we're doing 2 cubed cis, so I guess equals 3 times 120, which is just 360. So this is 8 cis. 360 is the same as 2 pi. 2 pi is the same as 0. So this is just 8. And I got that really quickly by thinking that 0 is here. So we have to go this way. And then 8 units. And like, where does that put you in the plane? That puts you at 8, 0, puts you at 8. Or, cosine of 2 pi is 1, sine of 2 pi is 0. So it's 8 times 1 plus 0i, so 8, no matter how you do it. This one, so what I'm going to do first is I'm going to convert. So negative 2 minus 2i, negative 2 minus 2i. So I guess I'll actually calculate r. I mean, it's 2 root 2. So it's 2 root 2. I'm going to write that as 2 to the 3 halves. And I got that by doing the square root of negative 2 squared plus negative 2 squared, right? So the square root of 8, 2 root 2. So theta, you can just look at it and see like you're cutting the third quadrant in half. So that's going to be 5 pi over 4. All right, so I want to raise this. So this is equivalent to saying that I want to do 2 to the 3 halves cis 5 pi over 4 to the 5th. All right, so that should be 2 to the power to a power, you multiply the exponent, so 15 halves. That's weird. Cis, now it's, you multiply, right, so it's n times theta. So theta is 5 pi over 4, n is 5, so 5 times 5 pi over 4 is 25 pi over 4. 25 pi over 4, so you want to think of 8 pi over 4 is 1 full rotation, so I'm going to do minus 3 times 8 pi over 4. So this is, it's coterminal to just pi over 4. Okay, so this is 2 to the 15 halves cis pi over 4. Okay, so the cosine and the sine of pi over 4 are both root 2 over 2. Right, cosine of pi over 4 is root 2 over 2. what I'm going to do is kind of weird. I'm going to rationalize the numerator, I guess, and say this is 1 over root 2, or 1 over 2 to the 1/2. The reason I'm doing that is that it's going to make this simplification easier, I think. 1 over 2 to the 1/2 plus 1 over 2 to the 1/2 I. So when you're dividing same base, you subtract the exponents. So this will be 2 to the 14/2, so 2 to the 7th plus 2 to the 7th I. So this, I think, is my final answer. I'm going to check it on the calculator and just make sure. 2 to the 7th, do I know that? 2 to the 5th is 32, so 64, so 128. This should be 128 plus 128I. We'll find out. So let's switch over to the calculator. So the calculator, again, it doesn't care if you give it something big to do. So do I have cis defined? Oh, I do. Okay, so if you don't have cis defined, you would do cis of t colon equals cosine of t plus I, which you have to use this pi thing for, I times sine of t. I think on the keyboard, maybe you can do at I, and yeah. So I don't know how that's not practical on the handheld, but if you're typing, you can always do at I and it will show up. All right, so I was doing quantity 2 cis, and then 120 I have to write as pi over 2 pi over 3 because I'm in radians, and then cubed, and I get just 8, which is what I had. So if I do -2 minus 2, I'm going to do the at I thing, and then to the 5th, I get 128 plus 128I, which is great. That's what we thought it was. If we do 2 to the 3/2, I mean, we already know this is going to work, but like, it's not terrible to do. 5 pi over 4, and then we raise that to the 5th. It'll give me the exact same thing. And then I guess just to show you, if I do cis of 25 pi over 4, I get this, and if I do cis of pi over 4, I get this. So that's why like all my simplifications worked as I went through it. I'm actually going to stop here because this page really is like 2 separate ideas. One of them is like, how do I raise complex numbers to powers? And then the other idea, actually, I think I wanted to go over to Chrome. The other idea is just let's do some practice problems. So I'm going to come back in the next video and do the practice problems. The other thing I wanted to show you was, and you should do this, all the time. Like, honestly, one of my favorite things when I was learning math, that like I've written all of these notes and I haven't included any of this in any of the notes because I don't want to be writing biographies and all these like little stories or whatever. One of my favorite things when I was learning math was in the textbook, there would always be a little box, and the little box would like have historical information or whatever. And you just learn all these like weird, neat things. So when you encounter something and if it has a name or whatever, like look it up, right? So here's de Moivre, which I think is how you say that. In math, de Moivre's formula or theorem or identity states that for any real number x and integer n, it holds that this is basically cis of x to the n is cis of nx, right? So this doesn't include the r. It says sometimes it's abbreviated as cis, and Euler's formula is involved. And here's de Moivre. You can click on him. I haven't done that before. I don't know. There could be some weird scandalous stuff. Who knows? Friend of Newton, Edmund Halley of Halley's Comet, Stirling of Stirling's formula, which you almost certainly don't know. I think it's Stirling of Stirling's formula. Whatever. Like, get involved in this. Go down the rabbit hole. You'll learn a lot of stuff probably. Let's see if Stirling is Stirling's formula. Stirling's formula has something to do with factorials. It's mind-boggling. Stirling's approximation. Let's see if it's written here. Actually, I don't know if we know enough math. Wait, where are you? You don't even have it? Let's click it. So a lot of notation. N factorial is approximately radical 2 pi n times n over e to the n. What? N radical 2 pi. So I mean, this video is over, but I'm gonna hold on. I'm gonna define that on my calculator, and then I'll switch over to the calculator. So we're saying, or he's saying, I am not signing off on this. 2 pi times n, and then n over e to the n. Okay, I don't know if that's what I remember as being Stirling's formula, but whatever. Let's go back to the calculator for a second. And again, this is just informational stuff, right? So that's saying n factorial is like approximately that. So let's do like 10 factorial. It probably gets better as n gets bigger. S of 10. Like, yeah. I mean, they're not like super far off. I don't know. 3 factorial. 3 factorial is 6. S of 3. It's like, not terrible. Well, 10 is not a big number, though. Let's do like 50. And then if I do 50 factorial, they're pretty close. What's the biggest factorial you can do on here? It might be like 255. No, I think it's like 450. It's one of the first things I always do on a calculator is figure out like what factorial can I do. 445 works. Does 449? 449 like sort of works, but it's in scientific notation. 445 might be it. Let's see. Nope, 446. 440. Okay, 446 factorial is the highest it'll get. Let's do S of 446. Hold on. That's interesting. I did approximately equal to, and it gave me this, which like, look at the first numbers, like 4283, 4283, like not bad. When I did an approximate version instead of like, no, when I asked for the exact value, it gave me infinity. So whatever. Anyway, that's Stirling's formula. Nothing to do with Moivre, except he was friends with Stirling. So that's a thing. But anyway, I'm encouraging you as you're learning math, when you see a name or you see a formula that has a name or a theorem or whatever, like look it up. Like Wikipedia has a ton of information on these things. The general internet has a lot of stuff. Anyway, I'll be back in the next video and we will continue with this page. So I will see you there.